See here, if the body changes its position due to the forces acting on the body, then the change in potential energy takes place. And see here, this change in potential energy is actually equal to the work done by the forces acting on the body, and this work done is independent of the path followed. Basically, that depends on initial and final position. That is actually the nature of the conservative forces. Already we have done in the work energy chapter. So, see here, now we have to define here gravitational potential energy. So, gravitational potential energy of a body is defined as simply defined as the work done in moving the body from one point to another in the gravitational field. Suppose you have taken a body here of mass m. Now, at a distance here x, a body of mass m is placed. Now, this body experiences gravitational force F is equal to g m upon x square. Suppose this body is brought from A to B by a displacement here, small displacement dx without any acceleration, then the work done can be written here g m upon x square into dx here. Already we have done these steps in the gravitational potential. So, now if you want to take the body from any one point to another, suppose from R1 to R2, where R1 is greater than R2. So, R1 is suppose somewhere here and you are bringing the body to this point, which is R2 from the center of the body, this capital mass m. So, we can write the work done dW is equal to g m 1 upon x square dx, here R1 to R2. Now, we can integrate it. When we integrate it, we will be getting it here g m minus 1 upon x R1 to R2. So, see here, we can write this, we can solve here this work done, and we will be getting work done is equal to g m minus 1 upon R2 plus 1 upon R1, and you will be getting W is equal to g m 1 upon R1 minus 1 upon R2, and this can be given as a potential energy U is equal to g m 1 upon R1 minus 1 upon R2. So, when the body is brought from R1 to R2, there is the work done, and that work done is equal to actually potential gravitational potential energy. You know here R1 is greater than R2. So, obviously, this potential energy is negative, and if you are taking suppose R1 is equal to infinity, then and R2 is equal to you are taking R. In that case, what will be the formula for this? You will be getting here U is equal to minus g m upon R. So, when the body is at infinite distance, its gravitational potential energy is negative, and now here when the body is at distance R, gravitational potential energy U is equal to minus g m upon R. Now, suppose the body is moved from surface of earth to the height h, then we can write R1 is equal to R and R2 is equal to R plus h. Then change in potential energy we can take here U, this is change in potential energy U is equal to g m 1 upon R minus 1 upon R plus h. We can take R common here. So, we will be getting g m 1 upon R minus 1 upon R into 1 plus h upon R, and here we can write g m upon R, here 1 minus, here 1 upon h plus R. So, we can write 1 plus h upon R raised to power minus 1. Now, we can use binomial expressions. So, we will be getting g m upon R, it is here 1 minus h by R. So, here g m upon R into 1 plus here, sorry, 1 minus 1 plus h by r, this and this will get cancelled. So, now you will be getting here this formula. Basically, this is coming delta U, that is change in potential energy, is equal to G m m upon h upon r square. Now, this you know that is equal to acceleration due to gravity. So, we can write here G m into h. So, that is actually mgh. So, when the body of mass m is lifted from the surface of earth to height h, then the change in potential energy is taking place, and that change is equal to mgh. Now, see this example related to gravitational potential energy. Suppose there are 4 masses placed at the 4 corners of a square of side L. Now, you have to find out gravitational potential energy of the system. So, now see here, first we will calculate its this is a diagonal. Diagonal will be coming here. Suppose you can take any one, that is a AC is equal to BD is equal to L root 2. And if you are taking half of the AC, so this is the center O, but that we do not need actually here. So, for calculating potential energy of this system, first we assume all the masses are at infinite distances. When all the masses are at infinite distances, their gravitational potential energy is 0. Now, suppose first when the mass, this one A, when the mass m is brought to the point A from infinity, the work done is 0, because there is no another body or there is no gravitational force of any other body except the earth. But when you bring the body of mass m to the point B, and this distance is L, this body has gravitational potential energy, and this potential energy is equal to, can be written here, U1 is equal to minus G here m into m divided by L. So, U1 is equal to minus Gm square by L. So, when the body of mass m is brought to the point P to the point B, then the potential energy is minus Gm square by L. Now, similarly, we bring the third body to the point C, then it has gravitational potential energy due to this and due to this also. So, that this distance we know that is L root 2. So, then the total potential energy can be written minus Gm square by L, this is due to this, and due to this is, here we can write minus Gm square upon L root 2. So, this is the potential energy of the body m at C. Now, if you are bringing the fourth body to the point D, then it has potential energy due to this and due to this, all these 3. Then we can write here U3 is equal to, that is the potential energy of the mass m placed at D, minus Gm square by L minus Gm square by L, this is due to A and due to C, minus Gm square upon L root 2. So, these are the U1, U2 and U3. This is the potential energy of the body B, C and D. Now, we can get the total potential energy just to add all these things. So, when you add all these things, you will be getting U is equal to U1 plus U2 plus U3. Now, see here minus Gm square upon L here, and these 2 are here. So, we can write minus 4 Gm square by L, and now this and this are here. So, we can write minus 2 Gm square upon L root 2. Now, we can solve it here, we can simplify. In that case, we will be getting, we can take common here minus Gm square by L, and we can take here common as well here, that is 2 also. So, we will be getting 2 plus 1 upon root 2. So, we will be getting here minus 2 Gm square 2 root 2 plus 1 upon root 2 into here L. So, this is the potential energy of the system of the 4 masses placed at the 4 vertices of a square.